Hello everyone. In today's lecture we are going to discuss about the two laws, that is, first one is Gay-Lussac's law and second one Avogadro's law. Now before going into those two, let us remember the laws which we studied in the previous lecture. That is nothing but the Boyle's law and Charles' law. That is, at constant temperature pressure was inversely proportional to volume. Now at constant constant pressure, the volume was directly proportional to temperature in case of Charles' law. Now the third one, that is Gay-Lussac's law. In Gay-Lussac's law, if we keep the volume constant, okay, if we keep the volume constant, that is, let's write that Gay-Lussac's law. If the temperature, if the volume is kept constant, for a given amount of gas, okay, for a given gas or given mass of gas, then the pressure and the temperature, how they are related, okay. I hope you remember the Charles law, when we said that if the pressure is kept constant, then volume was directly proportional to temperature. So similarly in Gay-Lussac's law, if the volume is kept constant, okay, for a given amount of gas or for given mass of gas, then the pressure is directly proportional to temperature. That is, P upon T equals to constant. So for temperature T1, if the pressure is P1, and for temperature T2, if the pressure is T2, then we can write P1 upon T1 equals to P2 upon T2, okay. That is under one condition, that is volume is kept constant for a given mass of gas or given amount of gas. We should not change the amount of gas and we should not change the volume, we should keep them constant. So under those conditions, the pressure would be directly proportional to temperature. If we change the temperature, the pressure changes. If we increase the temperature, pressure increases. If we decrease the temperature, pressure decreases. So from this relation, what do we get? Since P is proportional to T, so P upon T equals to constant. Removing the proportional sign, putting a constant or proportionally constant. So P upon T equals to constant, or P1 upon T1 equals to P2 upon T2. Okay, at two different temperatures, two different pressures. Now let's see the example and the graph. As you can see over here, that is, in this particular figure, as you can see, if when the temperature is small, okay, less, the pressure is also less. Now go on increasing the temperature. We have shown here using two burners, okay, 1, 2, 3, 4. So if the number of the burners are increasing, it means temperature is increasing. That is the meaning of the burners, okay. So as you can see in the first picture, that is when the pressure is 1 atm, there is only one burner. Now increase the temperature to 2 burners, means 2 burners means the temperature would increase. So in that case, the pressure becomes 2 atmosphere, okay. And now 3 burners, or the temperature is increased 3 times, then the pressure also becomes 3 times the initial. As you can see the last one, when the temperature is 4 times the initial temperature, the pressure is also 4 times. It means it is directly proportional, okay. Now let's see the graph. As you can see, the pressure is directly proportional to temperature. It means if the temperature increases, pressure should increase. Now over here, as you can see, there are 3 graphs, right? Blue, green and red. So all those are for different volumes. So as you can see from the first law, that is Boyle's law, that pressure and volume are inversely proportional to each other. If the volume is less, pressure would be more. If the volume is more, pressure would be less. So over here, as you can see, for the red graph, okay, or the red curve, the volume is more, therefore pressure is less, okay. It is downward, the pressure would be less for that particular volume. As we go on decreasing the volume, that is V2 is less than V3, so pressure for that particular graph is more, okay, and V1 is the least volume, therefore the pressure for that graph is more. So over here we just want to show that the pressure is directly proportional to temperature. If we vary the volume, for the process, one process volume will remain constant, another process volume will change, okay. So that way, if we change the volume for different processes, the pressure and time graph, the nature remains same, but the curve will have more slope if the volume is less, okay, or the line of the graph will have more slope if the volume is less, and it will have less slope if the volume is more. I hope that is clear to you. Now let's see the fourth law, that is Avogadro's law. Now the fourth law, that is Avogadro's law. What does Avogadro's law state? The fourth one, that is Avogadro's law. Avogadro's law states that if we consider equal volume of different gases. Now why I am considering different gases? Because if the volume is same, I mean the masses would be different. Why? Because the molecular mass, the composition of the different gases would be different. That is why the mass would be different. So equal volume of different gases, okay, different gases at same conditions, at same conditions means the pressure, temperature, okay, the pressure and temperature, this will be same, okay. At same pressure, same temperature, all the different gases or different types of gases, equal volume of course, will have equal number of molecules. What is that? Equal number of molecules, that is N1 would be equal to N2 equals to N3 if we compare or if we consider three gases. Now as you can see over here, the volume is 22.4 liter, okay, that is equal volume of three gases, helium, oxygen and nitrogen, okay. So now all the three different gases. Now as you can see, the pressure and temperature 1 atm 273 degree Kelvin, okay, 1 atm 273 degree Kelvin, 1 atm 273 degree Kelvin, that is equal volume of different gases at same conditions, that is the pressure and temperature same, that is 1 atm 273 degree Kelvin. And as you can see, they have equal, that is number of moles, 1 mole helium, 1 mole oxygen, 1 mole nitrogen, right. So helium, oxygen, nitrogen, all the three will have same number of molecules. So from here, what do I gather or what do we gather? That is number of moles also, N1 equals to N2 equals to N3, that is number of moles is nothing but number of molecules divided by Avogadro's number. What is Avogadro's number? One Avogadro's number is nothing but 6.023 into 10 to the power 23 particles, right. So number of molecules divided by Avogadro's number is nothing but number of moles. So as you can see, so Avogadro's number for all the gases would be equal. So if we substitute over there, okay, that is instead of N1, if I write N1 upon, instead of mole 1, mole 2 and mole 3, if I substitute N1 by Na, N2 by Na, N3 by Na, and Na gets cancelled, and that is nothing but N1 equals to N2 equals to N3, that is number of molecules of all the three gases of equal volumes, okay, of equal volumes at same conditions, that is pressure and temperature would be equal. I hope you understood that, right. Now let's see the graph. Like as you can see, volume equal volumes, right. So volume is proportional to number of moles, that is nothing but our equal volumes equal number of moles. So over here, if we plot the graph, that is volume versus moles, that is equal volume. If we go on increasing the volume of each gases, okay, but equally. So now as you can see 22.4 liters, suppose we make 44.8 liter, the number of moles also will be, or number of molecules will also be doubled, okay, that way. That is volume is proportional to the number of moles or number of molecules of the different gases. So that's what Avogadro's law states. I hope you understood. So that's all about the gas laws too, that is nothing but Gay-Lussac's law and Avogadro's law. I hope you understood. Thank you.